I will ask our next speaker to stand up. So this is Durga Malladi from Qualcomm. He's project manager for the LTE Advance in the corporate R&D division. He joined Qualcomm in 1998. He has been involved with Global Star GPS activity, HSDPA, HSUPA until 2004, I think. And after he has been leading the research and development activity on LTE and LTE Advance. Regarding the background, he has been involved with system design, standardization, implementation, and testing. And today, we will talk about LTE Advance precisely and how it will influence his 10 years future. Thank you.
Okay. Yeah. Perfect. Okay, good morning. My name is Durga Malladi, and I'm going to be talking about, we talked about a lot of the problems earlier in one of the presentations, and I'm going to be talking specifically about one of the kinds of solutions that we've been looking at for quite some time, and take a very deep dive into what are the things that come to mind when it comes to this solution over here. We call it as heterogeneous networks, and I'll explain the details of that. So, I've had the pleasure of working on LTE since the very beginning, and had the luxury of taking a look at exactly the kinds of things that started off in LTE, and then as we move towards LTE Advanced. It's very clear that back in 2004 when we started working on LTE, at that time there were some specific goals as to what is it that we wanted to accomplish. And as we moved towards the later part of 2008 onwards, it became clear that with the advent of smartphones, sometime around 2007 timeframe, that it became clear that even the goals that we had set for ourselves with LTE were not going to be sufficient to meet all the expected data demand that we were anticipating. So a new set of goals were created, and this time for LTE Advanced. And let's take a brief look at exactly what are the kinds of techniques which are a part of this thing, and what are the things that they really accomplished to solve. So one of the biggest and most important technique that actually came about in LTE Advanced, and that's something that we've been working on as well, is the flexibility of deployments in terms of both the kind of bandwidth that is available for LTE and the aggregation of the bandwidth in itself. So it's wider bandwidth, both in an intra-band and an inter-band technology, but it's not necessarily the same symmetric bandwidth everywhere. So you could have 5 and 10 megahertz bundled up together in different ways. And that sort of flexibility is extremely important. LTE, if you take a look at 2G and 3G, and quite a few of us in the room have worked on it for a long enough time, and then as we moved into 4G, it's amazing to see how LTE is the first, I believe it's the first cellular technology which started off with multiple antenna techniques from day one. It's kind of quite amazing. That was not the case for Release 99 WCDMA, that was not the case for HSDPA. But that was indeed the case for LTE, and that's quite something. Of course, for LTE Advanced, one of the things that we did was we said, okay, let's take it to a different level now. What happens to be 2 transmit or 4 transmit antennas, it's gone up to a significantly higher order, both uplink and downlink MIMO. And the third technique, which we believe is extremely important, is a much more flexible and a faster deployment of the network itself. And the way to do that is to have a mix of small and large cells. And why small cells? We'll talk about that a little bit, but basically a co-channel mix of different kinds of small and large cells. Picocells, remote radio heads, femtocells, and relays, and see how they can actually mix and match together to provide the kind of benefits that we want. And when we start doing things of this sort, then we create interference, but at the same time, when we manage that interference, it turns out that there are spectacular gains that one can accomplish over here. So we'll specifically talk about that now. If you take those features and actually put them in vertical silos, if you will, and take a look at what are the kinds of benefits that each of these techniques actually come to bring to question. So let's first start from the left-hand side. So there is the frequency dimension. So in the frequency dimension, there's more bandwidth, more kinds of aggregation, if you will, multiple carriers, multiple bands. In fact, in LTE today, there are 43 different kinds of bands, TDD and FTD put together. And I'm not even going to get into the band combinations that come into that. That's a spectacular explosion of the number of bands and band combinations. What it does bring to the table is, the first and foremost thing is capacity. We can split the capacity into different carriers. Some terminals will be capable of carrier aggregation and aggregating the bandwidth. And those terminals also benefit from a peak rate improvement. But one of the most important things is the actual capacity increase. And therefore, it's a higher bits per second. This second dimension is that of space. And if you take a look at it in space, then we've just added in multiple antennas, both on the transmitter side at the base station and on a device side. Now, devices are they are not what they used to be in 2007 when we were only looking at smartphones. These days, we must look at tablets. And it's not inconceivable that tablets will have more than 2 receive antennas. It's really not that hard to see that. What ends up over there is these very high peak rates. There is some capacity improvement, but given the fact that not all terminals have these large number of antennas, most of the improvement is really in terms of the peak rates, but not in terms of the capacity improvement. And that's something important to understand. What that actually leads us to is a higher spectral efficiency, bits per second per hertz. If you have the same amount of spectrum, you get a little bit more on top of it. The third dimension, where this is, and it's kind of critical, is changing the way we tend to think of the network. In other words, instead of just looking at the basic radio link itself, we take a look at the network topology. And what we do now is a much more flexible placement of small and large cells. The large cells, the macro cells, are typically very planned in terms of their deployment, but the small cells are the ones which we tend to place in multiple different locations wherever the capacity needs are. And this sort of a different network topology is what's known as heterogeneous networks. And this does not lead to any increase in the peak rate at all. But on the other hand, it improves the overall spatially normalized spectral efficiency, bits per second per hertz per square kilometer. And therefore, it's an improvement in the capacity, it's an improvement in the user experience. If I'm a user, I'm used to a certain experience, and now that there are a much larger number of cells, I'm usually closer to the network, and therefore I end up getting a much better spectral efficiency. And this involves the usage of picocells. Picocells is where we're going to talk a lot more about because these are outdoor deployments. But then there are femtocells and remote radio heads, and there are 2 techniques which are actually used about over there. So at this point, I'll get a little more technical into that specific concept. And let's talk about heterogeneous networks. So I think we all like these hockey stick curves, and we've been talking about this for a long time, but the interesting part is now this thing has indeed become a reality. It is a beast that we have to somehow face. In the last 2 or 3 years, we've had approximately a 2x improvement, or rather 2x increase in the data demand. And if you extrapolate that, that's where the 1000x capacity increase by 2020 keeps coming along. And it is not at all inconceivable to think of that. In fact, that's most likely going to happen, and we must have the solutions in place over there. The problem is, spectrum is often limited. You don't really have that much of spectrum. Of course, we must look for different ways of acquiring that spectrum. There are multiple ways of doing that. But given where we are today, if somehow an operator today wanted to increase the capacity by 2x by next year, you just can't rely on having the spectrum and all the devices with the same band support over there. So what is it that we can do in the meantime? Take it one step at a time. Instead of taking a look at the entire 1000x, take it 2x at a time. What we believe is that a new topology is clearly needed to cater towards this sort of an increasing demand. And this stems back towards one of the points that I made earlier, that the radio link improvement in general is slowing down. If you take a look at the basic bits per second per hertz, and the evolution from 2G to 3G was quite drastic, from 3G to 4G was a little less, and as we go from LTE to LTE Advanced, it's become even smaller in terms of what we are doing. We haven't really added something fundamentally new in terms of the pure radio link itself. There are no new codes, there are no new other kinds of MIMO techniques other than what have already been discussed. Even the bandwidth aggregation fundamentally is not a new concept in itself. So radio link improvements are clearly slowing down from that perspective. What we need to do is take a look at a different dimension. That's the only way to solve this problem. So if you take a look at the way to, we, Qualcomm, we are not an operator, we're not an infrastructure vendor, so we talk about it from the terminal standpoint, but from the basic perspective of what is the way of trying to get additional capacity, cell splitting is the way to typically go about it. We add more cells, we bring the network closer. The problem is that site acquisition, if you think about it, it's not always that easy, especially in places where the capacity is needed. You want to deploy something in downtown, you can't just go out there and start digging up and laying down the fibers to get to the backhaul over there and things of that sort. So site acquisition is a problem. And even the cell site distances, depending upon different geographical regions, they're quite small. There are parts in Asia where it's less than 200 meters. In North America, we are used to a lot more in terms of 2 kilometer site-to-site distance. But that's not exactly a simple way of doing it. It's kind of inefficient in terms of the way to go about it. What's important, therefore, is a flexible placement of small cells. Well, why small cells? Why can't I just take large cells over there? Well, there is a huge slide deck that one can get into what are the economics which are associated with the small cells. But clearly, the price difference between a small cell and a large cell is quite significant. So from a pure economical standpoint, it does make sense to actually go about it from a small cell perspective. The question is, how do we do that? How do we just place a small cell and be done with it? Is that how it works? Well, yes, but there's a little more to it. So this sort of a flexible placement is clearly a way to address the capacity needs wherever it's needed. And what has been done in LTE Release 10, as it is called, in LTE Advanced, is a few techniques, and new techniques have been added to the mix to make sure that this actually works very well. And I'm going to talk about those two techniques a little more. If we take a Release 8 LTE, for instance, we just add the picocells or small cells into the network, and that's pretty much it. But usually the terminals associate with the strongest SNR, the strongest link. What has been added as a part of LTE Advanced Heterogeneous Networks is the ability to associate not necessarily with the strongest cell, but associate with the cell that kind of makes sense. What it means is you associate with the cell which is lightly loaded. It's kind of intuitive to think about it that way. I don't want to be associated with a cell which is very strong if it's heavily loaded. I'm not going to get a huge amount of data rate over there. If I can somehow associate with a slightly weaker cell, but also lightly loaded, that's better. That is the key to everything in heterogeneous networks. And that's what, in a nice graphical manner, has been shown over here, the two techniques. One is range expansion. And I'm going to use that term a few more times over here, so let me just get to it immediately. Why do we say range expansion? Well, picture this. A macro cell typically transmits at anywhere from 20 watts to 40 watts. It has a large footprint, it's nice and large. Picocells typically transmit around 1 watt to 5 watts, much smaller. Now, the ability to increase the capacity really depends upon how many UEs or how many terminals can be a part of that footprint. If that footprint can somehow be larger, even with a 1 watt transmitter, that's important. And that's what we call as range expansion. In other words, more and more users get to be served by these picocells. And the way to do that is not by increasing the transmit power of the picocells, but you rely on the terminals to make sure that they can associate with this. And that's where resource partitioning comes in. So this is range expansion in a couple of slides over here. On the left-hand side, we have a limited footprint of the picos due to the macro cell. Let's not look at the words over there. The pictures are more than enough at this point in time. If you take a look at the basic coverage of the macro cell, it's fairly large. The picocells are kind of small. What we do is we make sure that there is some sort of a partitioning of resources which is done. It's more of an intelligent load balancing in the network. What it does, it allows the picocells to have a much larger footprint. And this is done in time domain manner, so therefore the network must have some notion of synchronous operation. It doesn't have to be globally synchronous, just in the limited region over there. What it does is it allows the terminals to associate with these smaller cells, but they are lightly loaded. And therefore you get to have a much larger bandwidth allocation typically allocated to you. And so how does this work? Does it mean that we have to, every single device in the network must move towards LTE Advanced? What happens with backward compatibility? Well, as always, in 3GPP, we have done this in a very systematic manner. We've made sure that backward compatibility is sustained. One of the nice properties, if you think about it that way, is if we have, let's say, 50% of the users, or maybe I shouldn't say 50%, 80% of the users are the legacy release 8 LTE devices, and only 20% of them are these LTE advanced devices. Well, as more users get offloaded to the small cells, even the legacy users get to benefit because now the original macro cells are lightly loaded, and therefore they also have an improvement in their overall capacity. That is the nice part of all of this. And in that sense, legacy UEs experience the same or better benefits along with the advanced UEs. And we don't have to go into the details of what exactly are almost blank subframes, ABS as they are called. That's a low-level technical detail, but suffice it to say that we must make sure that backward compatibility is maintained. And therefore, when the time domain partitioning is done, some signals are still transmitted by the macro cell, but it doesn't transmit any traffic. Meanwhile, the pico cells are transmitting the traffic. And I'm going to skip this part a little bit and talk just in the notion of time domain partitioning, the way it is done. And if you take a look at the figure and think of time domain on the x-axis, then you see that on the downlink, the macro cells, for instance, wherever the data is being served, that's being shown in blue. And the corresponding one on the pico downlink is shown in white. That's because it's not really served at that time. So you can ask yourselves the question, well, how did we really benefit from it then? All we did was we said, okay, 50% of the time the macro transmits and 50% of the time the pico transmits. Then aren't you simply trading off bandwidth in terms of the frequency and time domains? So is there a catch here, something that is missing over here? Actually, there is a catch. In fact, there is a good catch, because all the pico cells in the network, they all follow exactly the same pattern. So you end up, because if you have just one macro and one pico cell, there's no gain. But you add two pico cells, there's a gain. You add three, there's more gain. And in fact, it starts scaling up as the number of pico cells increase. And that is something that's important over here. So another way of looking at it is, well, who gets to control who has what? Again, as always, we want to have some notion of a method to this entire madness. We drop these pico cells all over in the network, but at the same time, the macro cells get to control, okay, who is doing what and where in a resource efficient manner, because that's where actually a lot of the information is. And that's what is done in the entire network. Okay, so those were the basic techniques. So let's get to the point. We said we wanted 2x improvement. Do we get 2x improvement? Well, what is the improvement that we are looking at over here? Typically, one should look at the entire CDF curve of the user throughput. But how do you quantify user experience in some sense? So we looked at two different metrics. One of the metrics is the median user throughput. 50% of the users get better or worse service. And the cell edge throughput. What we see is that this is based upon simulations, and I'm going to talk about the actual results itself. But if you take a look at the simulation analysis, what it shows is the green bars are the typical release 8 LTE, as in we just drop pico cells, but we don't do anything else. And we get a little bit of an improvement. This is a case where the users are uniformly distributed in the entire network. So it really depends upon which ones are close enough to the pico cells, and you get it. So you get about 20% improvement on the median and 5% on the tail. On the other hand, with all these new techniques, we are getting a 2x improvement overall in terms of the normalized spectral efficiency. Now, keep in mind that how did we get to this? We added more pico cells, so there is a cost factor associated with that. So as we start thinking about, okay, how much improvement am I getting as a function of the cost, that is important. So look at it in a different way. To get the same 2x improvement by using bandwidth, an operator would have to go and get yet another, let's say 10 megahertz of spectrum. So you have to compare the cost of acquiring yet another 10 megahertz of spectrum versus the cost of actually deploying these small cells. So you have to get deep down into the economics to see exactly where are the cost deltas over there. And that does become important over here. It's something to keep in mind. This is another case wherein we say, well, maybe uniform user distribution is not the right thing. Well, all my users, they sit in Starbucks, they have their coffees, and they're all over there. So those are my hotspots, and that's where I'm going to put my picos. Well, keep in mind that hotspots don't remain hot during the entire day. They grow hot and cold. What you have, the traffic pattern that is there in the daytime, shifts in the nighttime. It's kind of very inefficient to think in terms of a network wherein you only cater towards one part and not to the other part. It used to be that there was a notion of a busy hour. Now explain to me how busy hour works with someone who's watching Netflix at 7 o'clock in the evening. There's no such thing anymore as far as we are concerned. Those days are over. So you have to think, but anyway, in terms of hotspots itself. But what is interesting is those 2x gains that we are talking about in terms of the increase in the spectral efficiency, they're still preserved over there. This is good. Theoretically, it all looks good. We all like doing simulations. It looks nice. We submit this to 3GPP and it works well. Now, we're going to talk a little bit more about the simulations and then get to some actual test beds that we have built up. We've talked a lot about the downlink, and it was important to really focus on the downlink. Why? Because the traffic pattern, interestingly, has become a lot more asymmetric because of the advent of video downloads. I mean, that is something that's important. But what is also interesting is a typical smartphone, it's amazing to see the asymmetry that can and cannot occur. For instance, a year and a half back or so, we got a request from one of the North American operators saying, we have a problem in the network with the 3G network. It was primarily seen during, we love college football over there, so Saturday's college football time frame. The traffic is highly asymmetric, but in the uplink. That was an interesting one. Why would that happen? What we found was that the click and send the picture kind of a concept is used extremely by all the college students over there. So you take a picture of your friends and you upload it to Facebook. Well, that looks great, but the problem is now the traffic is actually on the uplink. A fundamental paradigm shift. You're not really used to this concept. We all think of video downloads, but this is like all in the uplink. More than 50% of the traffic was on the uplink. So it is important to therefore also analyze what's the benefits on the uplink. And it turns out over here there are some very good gains to be achieved with the uplink as well. If you look at it in a different way, with a 1 watt transmitter, a user has to be very close to the transmitter to actually associate with that small picocell, but the path loss is smaller to the picocell typically, and therefore overall transmit power is lower, or for the same transmit power you get a higher spectral efficiency. That's where these gains come in from. We call it as D1, by the way. You might have noticed it, D1 hotspot and D1 uniform. D1 is just one of the methodologies wherein we have a 500 meter side-to-side distance, 2 gigahertz carrier frequency, a typical European deployment in that sense. Again, the gains are preserved for hotspots. You can see these huge 2x improvement in terms of what can be done. For the North American deployment, which is kind of important for us, where the cell sites are much spaced apart, 2 kilometers, we no longer talk of like 2 or 3 picocells. We're actually talking of 5 or up to 8 picocells. So these are this is analysis that was done with 8 picocells. So the simulations look pretty good. So we were pretty happy with this, but this is actually old news in the sense that we had done this a while back. We said, okay, we've done all the uniform distribution, the hotspot distribution, and the gains look really good. But how do we know that there are these gains at all? We got to build it. You got to test it. You got to actually prove to yourself, only then you can prove it to the others that it can actually work. And that's what we did. And one of the important criteria that we looked at was, it's actually very easy to think about it that way. What fraction of the users can we offload? And in fact, that's where the difference really comes in from. If you don't adopt the techniques, there's only about 57% or so. But if you go towards, as you start adopting these kinds of techniques, the number of users who get attached to the picocells happens to be much larger. So, okay, so we thought this is good. On PowerPoint, it looks great. But how do we know this works? Can we really build it? We are talking of associating at very low SNRs. We don't do that. Typically, we hand over by the time it's like a 3 or 4 dB in terms of -3, -4 dB C2I. We say, well, it's no good, we need to hand over. Can we really sustain a terminal at -15 dB C2I? Is it possible? Can we build it? And if you build it, is it still power efficient? These are the things that we actually looked at. So we built up an over-the-air test bed in San Diego. And well, the primary objective was to show, first convince ourselves and then convince others that this is the way to go. And what we did was we like building prototypes. My team has been doing this for a while now. We did this for release 8 and now we did this then for release 10. We said, okay, let's build up the terminals. We have our own terminals. And we have release 8 commercial devices which we use in our network. Even though we are not an infra vendor, but we have to build our own some base stations to test our terminals. It's the easiest way to do this, but it's just prototype therefore base stations, just for ourselves. And we have leased some spectrum, which is in AWS band, and it's 10 megahertz and 2x2. And the This is like a high-level overview of how our testbed looks like in Sorrento Valley in San Diego. We have 2 macro cells, we have 3 picocells, 1 femtocell. We're adding a few more now, a lot more into it. The green and the red, you know, the coverage, that's not the coverage itself, that's just the azimuth, the direction in which the macro cells are pointing. But we have a pretty good coverage of the entire Sorrento Valley area over there. And we have pedestrian to vehicular speeds going to about 30 miles an hour or so. So it's about 50 kilometers an hour, that's the maximum speed. There is a freeway over there, but that's not something that we've been actually focusing on. Okay, so this is the testbed that we built up. And as I mentioned earlier, just to get an idea of the scale of this network, we're talking of the macro site, intersite distance is about 1 kilometer, which is just about enough for us. But the picocells are all over the place. Some picocells are at the edge of coverage of 2 macro cells. Some picocells are right next to one of the macro cells. So it kind of gives a very somewhat ad hoc but semi-planned kind of a deployment. And one of the most important things that we did was, okay, as we drive around and as we are stationary, what is the data rate that we can actually sustain at the terminal at what C2I? And it was really nice for us to see that we could go up to 20 megabits per second even at minus 12 dB C2I on the reference signals. That was the first proof that, okay, I think we are on the right track over here. So the simulations were good, but it's always good to see that working in practice. And what's even more important is, at minus 16 dB C2I, the terminals can detect these picocells way ahead of time, and they report it back to the network, and therefore it gives the network plenty of time to decide, should I hand him off to the picocell or not? Should I offload him or not? There are lots of time over there. And this was a little interesting because, you know, usually in analysis and simulations, we are very constrained by the path loss models that we pick, the channel models that we pick. It's usually coming in from academia and literature. But to see it working in the field is quite something. I mean, it's quite amazing. I always love sitting in our van and going around. It's really beautiful to see it working that way. And we have all these techniques that we talked about that was actually shown over here. So another way of looking at it is, as we looked at the picocells, we said, if I didn't do anything, what's the coverage of the picocell? And if I added these advanced techniques, what's the coverage of the picocell? So this is one example wherein if you take a look at the green curve over there in the middle, it's kind of hard to see. Hopefully you can make it out a little bit. But if you take a look at the green curve, the one that says Pico AM, AM is our building name, by the way. That's the only reason it's written that way. That's the nominal coverage of the picocells if we didn't do anything. On the other hand, if we use these LTE advanced techniques with what is known as the cell range expansion, that's the coverage of the picocell. This is actual live data that we picked up with our van driving around slowly in the parking lot, going back and forth. It is what it is, as in this is exactly what we came out from there. This is quite something. This is if you did only a small fraction of it. So this was a case where we could go up to minus 18 dB. This is if you did minus 6 dB. So why do we do these kinds of sensitivity analysis? It's just to make sure that there's no brick wall kind of a curve. It's a graceful degradation or an increase in terms of the capacity. And that's kind of important to do that we shouldn't be, any well-designed system should not be extremely sensitive to your assumptions. It has to be robust enough. So that's kind of important that we actually showed this. This is another of our pico sites. This is a very large range expansion that we had. This is one of the other pico sites that we had with the minus 18 dB, and this is at 6 dB, sort of a coverage, again a smaller one. So earlier this year in Barcelona and Mobile World Congress, we actually demonstrated these techniques in the booth environment, in our booth, showcasing how the capacity benefits come in. And it is in a cabled up environment, but this is over the air now. In fact, we'll be showing one of these demonstrations again in the upcoming Mobile World Congress in Barcelona. So you're more than welcome to come to our booth and take a look at this. So are we done with this? Does it mean it all works? We believe that yes, in principle and in practice, it works. For every operator, the choice really comes down to in terms of economics. Where exactly, how many picocells can you add in? Where can you add? And in what form can they add? But we believe it's a very nice technique to make sure we can get at least the first level of 2x improvement, squeezing out a little more from what we have with just the current bandwidth. Thank you.
No, no. Thank you, Dora. If you have some question, I mean, we have a short. Yes. Just quick.
Can you comment on the delay performance given you're doing time domain sharing?
You mean the time scale at which these sort of resource partitioning is done? Yeah, that's in the order of about 200 milliseconds or so. So it's important to have that not too large, because then the smartphone user experience is not quite there, but not too small, because otherwise you're chasing your own tail with interference. So you don't want to do that. So it has to be just about right. And we took some time to settle down at that sort of a delay.
So does it break down if you have higher density of picocells?
No. In fact, that's one of the experiments that we've been doing. So with 4 picocells, then we're adding more, and so far it looks pretty good. In simulations, we have not seen that, but even in practice, we have not seen that.
Okay.
I've one question. Meanwhile, they bring the microphone, I take advantage. What is the impact on the UE? I mean, if I have release 8 UEs and I apply these techniques, what is the impact?
So release 8 UEs do not benefit from this notion of range expansion, primarily because there are certain procedures that the UEs are supposed to do, RLM and RRM procedures, which are only defined for release 10 UEs. So release 8 UEs are not even aware of it. But they have the fringe benefits because the release 10 UEs have these procedures in place. They also have the ability to sustain high data rates at low C2Is. Given that they get offloaded, the release 8 UEs now benefit from somewhat lightly loaded macro cells. What used to be heavily loaded has now become lightly loaded, and therefore they benefit from it.
But they are not supposed to interference the pico cells in those time slots where they are not supposed to transmit?
Yes, in fact, they will not interfere. So clearly, because they are still being served by the strongest downlink, the strongest SNR, and in that sense, on the downlink, clearly there's no problem. Now on the uplink, they are being power controlled by the macro cell, and there's also interference management that's going on between the macro and pico cell from that perspective. So that is taken care of in that sense. One has to be, a little careful in terms of the way the interference management is done, but again, it's not. In practice, we have seen this as not really a fundamental problem.
You have tested in practice?
Yes, of course, yeah.
Hello, this is Jaime Yuk from Telefonica. One question is about, you mentioned about, for example, ABS and the possibility of making or having it some kind of flexibility and dynamics by talking between the macro and the pico layer. I think this talking between the macro and the pico layer is going to be key for the success of this, not only for ABS, but in general, load balancing. I mean, we need them to talk. Now, the question is whether we are working towards a scenario in which we could have different technologies from the macro and the pico. And by different technologies, I mean technologies coming, for example, from different vendors. Because if we, I mean, you mentioned one of the key things of the small cells and the heterogeneous networks will be the economics behind. So if we think on deploying much higher number of small cells when compared to macro layer, we may think on different kind of architecture and different kind of electronics. And we don't necessarily need probably to have the same vendor or the same structure in the macro and in the pico. Then my question is whether, and what is your vision in terms of the future, being able to have this interaction between the macro and the pico, but not coming from the same vendor, because today what we are seeing in the progress in our operations in the market is that we tend to go for a split of technologies on a regional basis, or to have all the technologies coming from the same side. But I think this is not good on helping the economics behind these models. So
I think you've touched upon a very important point, but let me address one of the topics that you talked about, that this sort of adaptive partitioning is key. But if you notice in one of the slides, we made an important assumption over there that while that is important, that there might be different kinds of vendors, it really depends upon the operator's choice and the basic economics. In some cases, it might make sense to go with the same vendor. Maybe in the beginning, it will be from the same vendor, and then slowly it will gradually open up. But the control of who gets what, how many resources get allocated to which pico and so on, it still resides upon the macro in this algorithm over here. And because of that, there are some dimensions in terms of even if you do want to go ahead as an operator, if you do want to go ahead and have these multiple vendors, you must make sure that first of all it works properly. But the nice thing is that not only the specifications, but even the way the algorithms work, they are done in such a way that a good fraction of this sort of a decision-making process is still done by the macro over there. It's good and bad. It's good because now you have more control on things. It's also bad because it really depends upon how you view your overall topology in some sense and how you envision your network coming up. But the techniques are, it is easily possible for that sort of a scenario to develop, absolutely.
Yeah, I guess there are mainly two scenarios. One scenario in which we have this kind of coordination and control by the macro layer. Another one that was, I think, introduced yesterday by one of the speakers is to have more autonomous way of doing things so that, for example, Pico layer would learn, which has some problems as we all know. So how do you think 3EPP evolving on that?
Yeah, actually, that's another point. If you take it to the limit wherein, let's say that there are 10 pico cells and only one macro cell, at some point in time you would reach a point wherein you say maybe that the balance of power has shifted a little bit more towards maybe the picos need to do a little bit more. I didn't touch upon one important topic called SON, self-organizing networks. Actually, there are a lot of these self-organizing features which are important for the pico cells. Why? Because you must view them as plug-and-play operation. You plug in a pico, you don't have to go in and plan the network. It must figure out what is the best possible cell ID that it should pick, what should be its transmit power and things of that sort. So those features do become important over there. The resource partitioning eventually, while it is initially done in the macros, eventually there might be other power elsewhere as well.
Thank you.